The transition to automotive application marked a significant turning point for a Miller cycle. Mazda led charge in 1990s incorporating a Miller cycle engine into their 2.3L kg Zim V6 demonstrating its viability. Passenger vehicles Subaru followed suit into integrating a Miller cycle platform engine into their hybrid drivetrain technology, further highlighting the cycle adaptability of potential of for energy with hybrid system. Modern implementation often incorporate sophisticated variable valve timing system, allowing for dynamic switching between Miller and Otto cycle, operating to optimize performance across diverse operating conditions. This flexibility has satisfied the Miller cycle position as a valuable tool for enhancing fuel emission in both large diesel engine and passenger cars.
What makes the Miller cycle different? At its core, the Miller cycle is very similar to the Otto cycle, except that the intake valve is held open longer or closed earlier depending on variant during the compression stroke. This valve timing change effectively shortens the compression process without reducing the expansion. Number 1. Intake stroke. As usual, the piston moves down, intake valve opens, fresh air and fuel mixture or just air in modern boosted engines enters the cylinder. Number 2. Partial backflow or delayed compression. Instead of closing the intake valve right at the bottom dead center, the valve remains open into the early part of what could normally be compression. Some of the incoming charge actually recirculates back into the intake manifold or stays lost in the ports until the valve finally closes. As a result, the effective compression ratio is lower than the geometric bore stroke compression ratio. Number 3. Compression stroke. Once the intake valve does close, the trapped charge is compressed from that point up to top dead center in preparation for ignition. Because the charge started compressing from a smaller volume, the compression work is reduced relative into the Otto cycle of the same bore and stroke.
Ignition and expansion. Spark plug is ignite the mixture just before the TDC. The expansion of the stroke still begins at TDC and pushes down the BDS ideally at the roughly same expansion. The ratio is an Otto cycle of similar dimension. That means you get thermodynamic rate on hot gases, even if you spent less work on the compensator. Exhaust stroke is a normal exhaust valve that opens the beard near of the BDC. That piston push the burns of gases out because the compression is cut short by keeping the intake valve open. But the expansion still runs off the full length of the bore. Stroke the Miller of the cycle achieve the higher effective expansion. The ratio compared to its engine peoples combine the Miller timing with a supercharge or turbocharging in order to keep the peak pressure where you want to be them.
Good day everyone. Today I'll be discussing the key thermodynamics effects of Miller cycle. An engine cycle developed to improve efficiency by modifying how compression is handled. First, the Miller cycle reduces compression work. This is achieved by keeping the intake valve open longer than usual during the compression stroke. As a result, some of the air-fuel mixture flows back into the intake manifold. This delays the start of the actual compression and reduces the effort required to compress the charge, saving energy. Secondly, the cycle maintains full expansion work, even though compression is shortened. Expansion still occurs from the top dead center to bottom dead center. This means the engine still extracts most of the energy from the combustion, just like in standard cycle. Third, these changes leads to higher thermal efficiency, since less energy is used for compression and more is extracted during expansion. More of the heat from the combustion is covered into a useful work, rather than being wasted as a heat. Lastly, there is charging penalty, because as long as the intake and charge is pushed back into the intake manifold, naturally aspirated engine would boost efficiency. That's why most Miller cycle engines are paired with turbochargers or superchargers, which help maintain the proper amount of air in the cylinder, despite the delayed valve timing. In summary, the Miller cycle increases efficiency by lowering the compression load, maintaining full expansion, and using boost system to offset air losses, resulting in a smarter, more efficient engine cycle.
The Attraction cycle is more fuel efficient than the Otto cycle because it allows longer expansion strokes but is produced less power, making it ideal for hybrid vehicles where electric motors assist with the performance. An example of a Texan cycle is used in the engine of the Toyota Prius, which uses this cycle to maximize fuel efficiency while the electric motor provides additional power when needed. So, one of the advantages of the Texan cycle is to improve fuel economy and ideal for hybrid system where electric motors compensate for lower power. So for the disadvantage of the Texan cycle is lower power output and more complex design, example variable valve timing or electric motor support.
The Miller cycle is much more closer to the Otto cycle but with a small change, which will be the intake valve. In the Otto cycle, the valve remains open as the piston retracts and closes as the piston contracts. In the Miller cycle, as the piston retracts, the valve remains open until the piston begins to contract again. This allows for air and fuel mixture to draw back inside the intake valve, allowing for more efficiency and more power output. Looking at the PV diagram or the pressure volume diagram, we have the processes of the Miller cycle. The Miller cycle differs from other cycles as it has 5 processes. The first process of the Miller cycle is the adiabatic compression or the processes 1 to 2 wherein volume decreases and pressure increase. During this process, there are no changes in temperature. The second process is the processes 2 to 3 or the constant volume process where heat is also added because of the constant volume and the rising pressure inside the compression chamber.
The third process is the adiabatic expansion process or the processes 3 to 4 wherein volume increases and pressure decreases. The fourth process, or also known as the constant volume heat rejection process, is where there is a loss of heat while the volume remains constant. The fifth process is the isobaric heat rejection process wherein there is a stable pressure while the volume is being decreased, preparing the volume of gases for the next cycle to begin. During this phase, heat is rejected naturally.